ठीक है, एक सेकंड भाग मैं। अच्छा, कहाँ पे के ये? अच्छा, दिस वाज व्हाट वी डिड लास्ट टाइम। ये हमने किया था कि दिस वाज द स्ट्रक्चर ऑफ बेंजीन। इट वाज अ bunch of double bonds and alternating double bond C6H6, ठीक है? Uh, but remember, I told you not to use this representation. What happened was that carbon was sp2 hybridized. Just a quick recap. ठीक है? So carbon was sp2 hybridized. Carbon was a trigonal planar. It was making three bonds. Three of its electrons, outermost electrons, were getting pulled in three different directions, while the fourth electron was buzzing around in the p orbital in the middle. So this is what happens when carbon is sp2 hybridized. Three orbitals, they turn into sp2, and one of the orbital remains exactly as it is. It just remains a p orbital. And alkene mein what happened was that they bonded together, right? They overlapped, and they ended up forming a sigma bond in the middle. Okay, there's an overlapping that's going to happen right in the middle. That's a sigma bond. So the sp2 and sp2 would overlap, forming a sigma bond in the middle, and the p orbitals, the unused p orbitals, they would start sideways overlap, which would result in a pi bond. Or मैंने कहा था कि this pi bond over here had very high electron charge density. The double bond had a lot of electrons in it, very, very concentrated in a very small area. So alkenes would strongly attract electrophiles. This was one very good thing about alkenes, that they had a lot of electrophilic reactions. They had a strong attraction for electrons. Not electrons, for electrophiles. They had electrons and they would attract electrophiles. Benzene was that it was exactly the same like an alkene, except for the difference that the overlapping that was happening was all over the place. Okay, so you had a p orbital, just like you still have a p orbital. The carbon is sp2 hybridized, so one electron goes over here, one electron bonds with this one. One of carbon's electrons, out of four electrons, one of them bonds over here. And there's an unused p electron. Now, this p orbital and all of the carbons were exactly identical. So what would happen is that not only would this p orbital overlap on the left side, it would also overlap on the right side. So basically, at the end of the day, there are six carbons, all of them identical, all of them sp2 hybridized, and they would all start overlapping. So this is your, इसके ऊपर लिख देते हैं, this is your p and p overlap. ठीक है, that's your sigma bond, so that's your sp2 overlapping with another sp2. And the hydrogen, that's basically an s orbital overlapping with carbons sp2. ठीक है, so those are all your sigma and pi bonds. And I told you you're going to get a big question on this, and this was the delocalized electron ring was represented by this. Or next time, make sure you kind of remember the easy way of knowing this is that they're alternating double bonds that kind of get mixed up. तो वो draw करना easy होता है, but alternating double bond, that's not the correct representation. So ये clear है? Is this thing clear, Ibrahim, Hala, Minal? Is this clear what benzene is?
Yes.
Yes,
ठीक है.
sir.
अच्छा, अब इसमें one important thing is that since the p orbital partially overlaps on the left side and its electrons are also overlapping on the right side, so the electrons are more distributed. So the electron density is not very high. Yeah, that's a major difference. So the p orbital, it overlaps on both sides. So its electrons are more distributed. So the electron density is more distributed, it's more spread out. So therefore, there's going to be less, unlike alkenes, there's going to be less attraction for electrophiles. Although it's the total number of electrons are more, but there's just a lot of delocalized electron cloud, but there's going to be less attraction for electrophiles because overall the charge density is all over the place instead of being concentrated in a small area. वो alkenes के मुकाबले, if you look at alkenes, the electron density is like I mean the overlapping is happening and the electron density is like concentrated over a very small area. There that's not the case, okay? So remember this, keep this in mind. Huge difference in electron density, okay, between an alkene and a benzene. Is this clear? ये clear सारों को?
Yes, sir.
अच्छा, उस पे वापस आते हैं. We'll come back to benzene. We'll just quickly recap what alkenes are because they're always going to compare it with alkenes. So I'm going to do alkene reactions quickly. Okay, remember this is very important. All this is all AS. But very important, all of their reactions are what they call electrophilic addition. So I'm going to go through all the reactions very quickly. You had hydrogenation. Okay, that's number one. So if you have an alkene, it will get hydrogenated and there would be a double bond and hydrogen would get added to it. So the reagent is hydrogen and the product is going to be, ठीक है, all reactions are with a double bond. तो ये जो आपका molecule है इसमें the only thing is that H atoms are going to get added to it. So there's going to be an H that's going to get added to this. An H that gets added to this one and the double bond in the middle goes away. Okay, so that is hydrogenation. The conditions are that you need a nickel catalyst. And the temperature has to be nickel होता है, palladium catalyst भी होता है, ठीक है? And the temperature is 150 to 200 centigrade. ठीक है, nickel or palladium catalyst. अच्छा, second one. ठीक है, that's the first reaction. Second one. So the first reaction, the only importance is that you have an unsaturated molecule. And that unsaturated molecule then turns into a double bonds खत्म हो जाते हैं, saturated molecule. As the second reaction, that's bromination. So उसमें क्या होता है कि you have an alkene and kind of the same thing. So I'm just going to copy paste इसी को copy paste कर लेते हैं. अच्छा, so instead you have bromine. And bromine atoms get added to the double bond. That's it. Or normally क्या होता है, it's Br2 aqueous. So either aqueous or inert solvent. The example of inert solvent is CCl4. ठीक है, or RTP, room temperature and pressure, no special conditions required, and you could have it same reaction with Cl2 as well. As a bromination, you've studied bromination since O levels. The importance is that it's used as a test for identifying unsaturated molecules. So test for unsaturated molecules. and the result is that the red, brown, or orange bromine decolorizes. So, okay, number 3, that's hydration. So what happens in hydration is that, well, something similar. So you have an unsaturated molecule, and this time water gets added to it. And अच्छा अब एक जगह पे ना H add होगा, and the other side it's going to be OH. And now you're going to get two versions. It's an asymmetric molecule. It's an asymmetric alkene. So you're going to get two molecules. One is this, that the OH adds at the end. Copy some. Second. And the other option is OH यहाँ हो जाएगा, H on the other side, right? The conditions are that you need 300 degrees centigrade temperature and you need 60 atmosphere pressure and acid catalyst. So it could be, normally it's phosphoric acid. अच्छा ये हो गया. अच्छा, now the important thing is, मुझे बताओ कि इसमें which one is the major product, which one is the minor product?
So the one that is bonded, like with the H bonded to more H's, will be the major product. The second one is the major product.
So this is your major product and the other one is our minor product. इधर add कर लेते हैं. That's the Markovnikov's rule. So H bonds to carbon already bonded to more H atoms. Let's see, okay, that's hydration. And the fourth one is hydrogen halides. Like HCl, HBr, HI. I said something similar would happen in, well, इसमें भी Markovnikov's rule होगा, ठीक है? Something similar would happen and अच्छा, with HCl, HBr or ठीक है, same thing, major and minor. So if you have it with HCl, so the H can bond over here, the Cl could bond over here, or the H could bond at the end and the Cl could bond but the H likes to bond with the carbon that's already bonded to more H atoms. So right while it's bonded to two H's, the left one over here is only bonded to one H, so or directly bonded to it. And this one normally usually happens at RTP as well. Okay? So keep in mind the Markovnikov's rule. Okay? Hopefully you already know what asymmetric alkenes are. So there were these four reactions, which were addition reactions, electrophilic addition reactions. Or secondly, you need to know the mechanism for electrophilic addition. So Smena, I'm just going to add one tiny detail, which is, so we can do, so here's my asymmetric alkene. And let's say it's reacting with HBr. So the positive H is going to, HBr kar lete. So the positive H, it's a polar molecule. The bromine is slight negative. It's already a polar molecule. It's going to get attracted to the electrons in the double bond, and it's going to be very strongly attracted to these electrons. Remember, we just discussed that the electrons over here have a very high charge density because they're very concentrated. So the negative charge over here, that's a lot. So which means there's going to be very strong attraction for H, and the electrons over here, because they've got a high charge density, they're going to repel these other electrons very, very strongly. So the polarization in this case is very strong, and you get your intermediate carbocation. So your intermediate carbocation is so the H over here will get attracted to the double bond, and it will bond with one of the carbons. And the other carbon will become electron deficient because the H came and took the electron, so it became electron deficient. And it became a carbocation. It could have been the other way around as well. While the Br at the bottom, that got a negative charge, and it became a nucleophile. And that Br nucleophile would come in and would then be attracted to the carbocation. Okay? So that's your carbocation intermediate. And finally, you're going to have your final product, which is going to be कि बस दोनों attach हो जाएंगे. The H is already attached, and the Br is now going to get attached to it. ठीक है, इसको अच्छा ये कर लिया. ठीक है, तो ये क्लियर है कि this is and this middle one has two options. You could also have the other option as well, where the opposite might happen. कि the Br can come and join. ये जो Br है ना, ये वाला, एक सेकेंड. अच्छा, the other option is कि this goes over here and ठीक है, that's the other option. ठीक है, this is your major carbocation. The H likes to bond with the carbocation and that's your minor one. So Skipper, this is probably going to be formed in lesser amount, and the first one would form in a much higher quantity. And the reason for that is the reason for Markovnikov's rule. If they ask you to explain the Markovnikov's rule, तो वो क्या होती थी कि you get a more stable carbocation if you have more electron donating alkyl chains. So the reason for Markovnikov's rule is that a 3-degree carbocation is more stable than a 2-degree carbocation, which is more stable than that's the number of alkyl chains that the carbocation is going to have. यानी अगर ये भूल गए उसमें कि you've got 2 carbocations, this one over here, the first one, has 2 alkyl chains. The one over here at the end, that's got 1 alkyl chain. ठीक है, जो उसके left पे. So the one that has more alkyl chains, that's more stable compared to the one that's got fewer alkyl chains. So if anyone is going to ask you about the reason, तो उसमें क्या होगा कि a carbocation with more alkyl chains which are electronating have lesser electron charge density and therefore are more stable. So basically what happens is that they have so much the carbon atoms on the right side and on the left side, so the charge over here decreases a lot. Which is why it's easier to form, because if somebody has to steal electrons, like H over here is stealing electrons, they can let go of those electrons because the positive charge is not going to be very strong. So which is why it's going to be easy to form. Okay? It's easy for H over here to steal electrons from this double bond because a positive charge would develop, which is not going to be very strong. Why would it not be strong? Because it will get electrons from the neighboring alkyl chain. So it will let go of the electrons in the double bond. तो इसलिए tertiary carbocations are easy to form. ठीक है, ये clear है? ये पुराना ASCS is clear?
Yes.
अच्छा, अब ये कि the important thing is this reaction over here needed no help. There was no catalyst, there were no conditions. It was just happening at RTP. And the reason for that is that the double bond has a very high charge density. ठीक है, वो हमने पहले जब structure पढ़ा था. So the reason you have a pi bond which has a very high charge density because the electrons are concentrated over a very small area. So they have a very high charge density and they can polarize the molecule. तो ये add कर लेते हैं कि so for alkenes, since the pi electron cloud has very high charge density, so therefore what happens is uh so polarizing the electrophile is very easy. Polarizing and attracting so they strongly attract electrophiles is very easy. Hence, normally the conditions that are used are very mild. So alkenes undergo electrophilic addition, and they very readily undergo electrophilic addition. ये खत्म हो गया electrophilic addition of alkenes. ये clear है? It's all AS, ठीक है? The only additional thing that we did was कि भाई alkene के पास pi electron charge density that's very high. So it's got very strong polarizing power and it can attract electrophiles. ठीक है? Clear है? हाला clear है? Minal, Qasim, Ibrahim, clear है ये?
Yes.
बाकियों clear है? Ibrahim clear है?
Yes, sir.
अच्छा, आ जाओ उस पे. अब now we're going to come to benzene. ठीक है? Their reaction is known as electrophilic substitution. And remember this thing? I said we're going to group all the electrophilic substitution reactions together. I said this thing is something that's very important. ये मतलब main चीज है electrophilic substitution of benzene. So we studied benzene, and if I just copy paste a benzene molecule, कहाँ गया पूरा structure draw कर लेते हैं. इसमें से I'm going to गलत हो गया. चलिए. ऐसा बेंजीन पे आ जाते हैं. I'm going to pick this. इसको थोड़ा छोटा कर लेते हैं. And let's remove the non-essential stuff. ये पता नहीं. हो गया. Achha, now look at this structure. Remember, I told you that the pi electron charge density is now not unlike the double bond, it's not very large. Achha, so when a bromine molecule approaches it, so it doesn't really get polarized. Okay, so the bromine molecule approaches it. I mean, it does get polarized. It was essentially a non-polar molecule. I said it was essentially a non-polar molecule, but हुआ ये कि because you've got a lot of electrons over here in the benzene electron cloud, those electrons are going to so they're going to slightly push or repel the electrons. Okay, that's what's happening. So one of the bromine becomes negatively charged, and the other one becomes positively charged. Okay, so polarization happens. And the positive bromine is going to start attracting the electrons from benzene. Except with one fact, because the polarizing is not going to be very high. The pi benzene ring or pi electron cloud ring has low charge density. So there is very less polarization that's happening. And if the electrons are like very distributed, so they're not going to attract this positive bromine towards themselves. So the attraction is not strong enough and there's no reaction. Okay, so on its own, there's going to be less polarization, and therefore there's no reaction happening. And unlike alkenes where polarization was like really strong. One of the bromines over here was very strongly positive. The other bromine was very strongly negative. And the positive bromine, because the electron density was concentrated over a very small area, the positive bromine was very strongly attracted to the electrons, which is not going to be the case over here in benzene. Ye clear hai? Ibrahim Hala, Qasim Minal, is this clear?
Yes, sir.
So the first thing is you would need a catalyst. Because the polarization is not strong. So the catalyst that you use is, for example, for bromination, it's going to be FeBr3. The good thing about transition metals as catalysts is that they have transition metal property. I think they don't. They've got a huge number of protons, which is why they don't lose electrons. They tend to gain electron. मतलब जैसा copper होता है electrolysis में हमेशा electron वापस gain कर लेता है. So gold doesn't like to lose electrons because the nucleus has a lot of protons. So transition metals have this tendency to form dative bonds, coordinate bonds, and they, जो भी हमने transition metal वाले chapter में पढ़ा भी है, they attract electrons. So what's going to happen is that this catalyst that you added, okay, this catalyst started to attract electrons from the other side. ठीक है, उसने दूसरी साइड से it started attracting electrons from the other side. So that kind of helps in the polarization, because polarization was not possible by just one benzene over here. That was unable to sort of push the bromine electrons to one side. Catalyst, on the other hand, is doing the rest of the work, and it's trying to pull the electrons from that side. ठीक है, तो ये क्लियर है कि अब इसमें ना पोलराइजेशन के लिए यू नीड हेल्प. ये क्लियर है?
Yes.
और उसकी वजह से क्या होगा कि it's going to get polarized. This bromine with its electrons is eventually going to be pulled by the FeBr3, and together they will eventually form a dative bond. So ये bromine जो है ना, it's going to take its electrons just like a complex, metal complex. So that bromine is going to take its electrons, and that bromine is going to datively bond with this FeBr3. And that Br is -1 because it took all the electrons, so which is why this entire thing will have a negative charge. So it's going to have a -1 charge. I said this Br, which is now not slightly positive because now it's fully polarized, it's a +1 ion. वो जाएगा and it will start attracting electrons from the benzene pi electron cloud. So it will, so one of this p orbital over here, one of this, जो कि overlapping कर रहा था, that will get attracted to this Br and it will bond with it. तो होगा ये कि ये pi electron cloud में से ना बीच में से गायब हो गया. ठीक है, so one of the carbon is no longer sharing its p orbital with the rest of them. Instead, its electrons are now attracted and bonding. I mean, it's carbon के जो electrons है ना, they're now bonding with this Br. TNBr is no longer going to be positive because it got the electrons, right? Meanwhile, वो जो आपका वो था ना benzene electron cloud, that has lost an electron, so that electron cloud will be positively charged. वो Br उधर कोने से है, it took the electrons, right? This Br. तो ये clear है? Is this thing clear?
Yes.
ठीक है, इब्राहिम कासिम, is this clear?
Yes, sir.
तो चलो ठीक है, इसको फिर कल कंप्लीट करते हैं. ठीक है, अभी और भी आगे, तो फिर कल कंप्लीट करते हैं. जस्ट रिमेंबर के over here in electrophilic substitution the molecule wasn't getting polarized, so which is why you needed a catalyst unlike alkenes. ठीक है, तो ये फिर हम कल कंटिन्यू करते हैं यहाँ से. चलिए ठीक है,
Okay,
ओके
Allah.
एवरीवन, अल्लाह हाफिज.